And then the recording. Okay, hello everyone. Welcome to our first press event of AGU23. This media roundtable is the Heliophysics Big Year, solar eclipses, exciting missions, and collaborative science, and more. Before we get started, a couple of notes. This is being recorded. You will be able to find this recording and the slides for the session in the press information exchange, which my colleague Becca here will drop the link to in the chat. If you have any questions or any problems and you're online, please drop a note into the chat or email us at news@agu.org. Our lovely panelists here are going to give you a very brief introduction to what they do and who they are. And then we're going to open it to Q&A both in the room and online. So if you are online, we hope you'll feel comfortable turning on your camera. A reminder that this is a Zoom meeting, not Zoom webinar, so you should mute your mic unless you want to be talking. And you can just jump in and ask a question or wave your hand at us and we'll call upon you. And I think that's everything from us at AGU. I'm going to turn it over to Sarah Fraser from NASA to introduce her panel.
Hi. So yeah, my name is Sarah Fraser with NASA's Office of Communications. I will actually let our panelists introduce themselves. So I will just start by handing it over to Kelly Korreck.
Hi there, my name is Kelly Korreck. I am the, we can go to the next slide. I am the program manager for the 2024 total solar eclipse. Next slide, please. And I am here and so excited to talk to you about the Heliophysics Big Year. The eclipses are a part of that and milestones within that big year. So the big year is really to emphasize that the sun touches everything, and we're challenging you to experience the sun in as many ways as possible. So this big year kicked off with the annular eclipse on October 14th, 2023, the total solar eclipse, which happens on April 8th, 2024, just under 4 months away now. And then this big year will close out with the closest approach of Parker Solar Probe, the humanity's mission to touch the sun, and will be the closest human-made object to the sun, December 24th, 2024. Next slide, please. During the eclipse, NASA has several priorities, the first of which is safety. So we want to make sure that folks are safely viewing the sun. And we also want to have broad participation. And we do science and exploration. So we are doing science in a variety of different ways. And you'll hear other folks talk about the science that's going to happen. But one of the exciting things that is happening is launching 3 instrumented sounding rockets into the eclipse. Out of Wallops. And so those will be an exciting thing on April 8th. And the next slide. We will also be doing a broadcast from various locations along the path. The map you see there is a NASA map with the line of totality going across 13 different states. We'll be spread out to show folks the path of the eclipse and to engage the public in those various locations. Next slide. I'll turn it over to Liz.
Hi, I'm Liz McDonald. I'm the Heliophysics Citizen Science Lead, one of my many hats. Next. So I can tell you that we have a whole array of participatory, also called citizen science projects where the public can participate in the Helio Big Year. We want to encourage people to try as many of these as they might want or that could catch their interest. I just realized my little slide could be organized by the first row are the helio-specific projects looking at the sun's corona that you can only see during the eclipse, the birth of the solar wind there. And it's very cool that we have an array of projects studying that with an array of different technologies, ranging from teams that are going to field some pretty fancy telescopes, to cameras, to an app, the SunSketcher app, where people can take pictures, and there's kind of different science goals for all of those as well. Then the next row, we also have projects focused on the eclipses, but on other effects. And the first 2 are very kind of educator school friendly, eclipse soundscapes, looking at the other things and senses, ways that we can sense what the eclipse is doing and the effect on the life around us, and GLOBE, which also measures the temperature and cloud changes during the eclipse, and then some ham radio, amateur radio projects. And then the last of sort of the bottom corner there are other projects you can participate in during the big year. Both indoors using just a computer, those are the projects on the bottom row, or outdoors, and those are kind of the ones on the lower right corner that we can't fully see there. But it will be an active time, the sun will be active, there will be more aurora, and there's a variety of ways that people can participate in citizen science. On the next slide, you can see our annular eclipse observations provided both some valuable science and tested protocols and training this past October. So you can see the Eclipse Soundscapes project, the telescope array for the Dynamic Eclipse Broadcast Initiative, some of the ham radio team, and some of their data, and then the Sun Sketchers cell phone photo of what they're looking at, the shape of the sun from all of these different cell phones. And really, having people all along the path is going to be a force multiplier for these observations and enable us to take longer observations and more correlate what's happening and changing. And the little things I sort of circled there probably reflect my bias as a scientist, because the ones on the left are kind of the tech, the audio recorder on the upper left there, and then the telescope, and then the data itself sort of on the right-hand side. So I'm happy to talk in more detail about those sorts of things. And the next slide, passing it on to Dr. Nir Caspi from Southwest Research Institute, who is also one of our citizen science PIs and doing multiple things.
Well, thank you. I guess I don't need to introduce myself. Thank you, Liz. I'm Amir, and Liz introduced a lot of very interesting eclipse stuff, so I'm here to represent two of those eclipse projects. One of the difficulties of an eclipse is that it's very fleeting. If you're in one place, you only get to see it for a few minutes, and there's a lot of science that can be done if you could only extend that time. So this year we're running two missions to basically chase the eclipse and extend the time in totality. On the next slide, you'll see the graphic. This is a composite graphic. It's not actually live, but that is for NASA's WB-57. So you may remember in 2017, we flew both of NASA's WB-57 jets with telescopes in their nose cones to chase the eclipse and observe it with visible light and infrared cameras. And for 2024, we're doing this once again, although this time with three brand new experiments. One of them, which I'm leading, to do multispectral imaging, so infrared, visible light, ultraviolet. One of which Shadia Habal from the University of Hawaii is leading, to do spectroscopy in ultraviolet and visible light. And one of which Bharat Kunduri from Virginia Tech University is leading, to do ionospheric sounding and to see how the Earth's ionosphere reacts to the total solar eclipse. And the reason that we're flying airplanes, besides the fact that it's really cool, is because getting up into the atmosphere, above the atmosphere, means that you can actually access wavelengths that you can't do from the ground, like the mid-wave infrared, like ultraviolet, that would normally be forbidden from the ground. And of course, flying an airplane means that you get to chase the eclipse, literally, and you get a few extra minutes of eclipse time in totality. On the next slide is another effort that we're doing, which is to have the eclipse chase us. So if you want to keep up with the eclipse for an hour, that requires a supersonic airplane, and that has complications all its own. But instead, if you deploy 35 teams of people along the path from Texas to Maine, you can have the eclipse chase you. And then as long as you outfit them with the same equipment, the same cameras, the same training, and they all take the same compatible data, then you can put it all together into an hour-long observation of totality. And that's what we'll be doing this time. This is, of course, leveraging work that was done back in 2017 under Matt Penn for that Citizen Kate project. This is the next generation Citizen Kate project, which will look at the sun in polarized white light. So we're going to be measuring the polarization angle of light coming off the corona, and you can see that represented in color in that middle image there, which was taken by one of our beta tests for the Australian eclipse in 2023, earlier this year. We are recruiting now, by the way, so please visit that website, visit the social media handles, and please consider applying. And I think the next person is Dave.
Oh, so good afternoon, everybody. I'm Dave Fritz. I'm with the GATS office in Boulder, Colorado, and I'm the project scientist on the NASA Heliophysics atmospheric waves experiment. So our motivation is that gravity waves that arise from tropospheric weather from very small sources can grow in amplitude enormously because of the decreasing density, and so they can have enormous effects at high altitudes. So our instrument is going to look down from the space station. It's already there, in fact, and it's been making measurements for about 3 weeks. And we will use those data at 87 kilometers to guide models that will enable predictions of these waves propagating to very, very high altitudes. So NASA has a prior release consent form. They won't share any data right now. So instead, my first slide shows some of these waves that have been imaged over Scandinavia from a camera in northern Germany. This is a field of view that is about 100 kilometers across. You can see the waves propagating from bottom to top or from south to north. And these likely arise due to convection that is occurring much further to the south, perhaps over Germany. What is interesting here is that the polar mesospheric cloud layer is very thin, so it allows us to explore very small features in the field. You can see very small oscillations at the bottom. Those are Kelvin-Helmholtz instabilities, and it's instabilities of the waves at large amplitudes that drive their breaking and momentum deposition and local heating and mixing. And so it's those dynamics that also happen at much larger scales at higher altitudes that will have, I think, very important impacts in the thermosphere, the ionosphere, and the lower space weather in environment. So there's even the potential that capabilities like this might contribute to predictive capabilities down the road. So this is an image of the AW instrument viewing in the nadir at the left, and the image at the right is an artist's conception of the International Space Station flying over the Earth, imaging at night of a gravity wave perturbations in temperature that allow us to quantify the waves and use those to seed our models, allowing us to look at higher altitude consequences. Great. I think it's under Dr. Noor Rao from APL.
Thank you. So, if we go to the next slide. I'm Noor Rawati from the Johns Hopkins Applied Physics Lab. I'm the project scientist at Pakistan Pro. When you go to observe the eclipse next year, think of a great spacecraft that will be flying through the same structure that we are seeing with the naked eye during the eclipse. That spacecraft is Pakistan Pro, and it's great because it's flying through an extremely harsh environment, and that environment, we go to the next slide, please. That environment is so hot and so violent that we need extreme technology to fly through it safely. If we now go to the next slide, please. The solar corona by nature is so mysterious, and one of the big mysteries that is over 8 decades old now. It is over 300 times hotter than the solar surface. And that is absolutely counterintuitive because from everyday experience, if you get away from a heat source, it cools down. It doesn't work for the solar corona. Go to the next slide, please. So another phenomenon that is also extremely complex that was predicted by Gene Parker, the namesake of the mission, and he predicted it over 6 decades ago. We have this flow of ions and electrons that is flying up to 2 million miles per hour. But when you look very close to the sun, these particles are almost standing still. The mystery, where do they get the energy to be accelerated so fast and to fill the whole hemisphere? Click next, please. The other big elephant in the room as well is solar activity. That is drives all the space weather, as you see it here, in flares and CMEs. And now, in particular, that we are thinking to send women for the first time to the moon and send men back again and land them there and maybe have a permanent presence there. Space weather that is driven by flares and CMEs take an absolutely new dimension. It's not only us here on the ground and the geospace, but it's all out there. And even if it takes another meaning, if we want to win the race to Mars, then we have to have awareness of space weather all over the place. And that's missions like Parker Solar Probe are helping us to understand how the sun works come in. If you go to the next place, please, the next slide, please. And the crown jewel of the Big Year is December 24, 2024, next year. That's when Parker Solar Probe will hit the closest approach to the sun ever. This is a monumental achievement for all of humanity. This is equivalent to the moon landing in '69. Now we are basically almost landing on the star. Thank you, and I'm happy to answer any questions.
Great. Well, those are all of our intros we have, so I think we're ready to take questions. In the room, if you just want to raise your hand and give your name and affiliation, and if you are directing your question for a specific person, and then I guess Liza or someone will let us know if we have questions from Zoom. All right.
Shall I kick us? Go on, you go.
Matt Sikowski from the Weather Channel. Kelly, I was interested in the 3 rockets that are launching off of Wallops. What instrumentation and the sort of the time period during the eclipse that they'll be taking off in?
Yeah, so that is the APEC mission, and they will be about 35 minutes before, during totality, and then 35 minutes after. So it is also focused on the ionosphere. Most of our science on Earth is focused on the ionosphere, and that sudden day night that actually collapses it gives us a lot of insight as to what happens when it's otherwise perturbed. We really like the ionosphere because that's how we communicate in multiple different ways. So we want to study it, and we are measuring things like air temperature, density, and seeing how that changes. There's also some radar they're using from the ground, and balloons as well. There's all sorts of stuff going up to study the eclipse to really get that full picture of what happens to the density and to the wind speeds and temperatures at that altitude.
Thank you.
Yeah, a couple of questions. How does this eclipse compare to 2017? I mean, not all eclipses are the same, right? Different tracks, go over different population areas, different seasons, different cloud fraction, all the rest of it. I mean, I'm just wondering, is there a way to compare this event with the one that we had in 17?
Yes, so in 2017, there was a lot of, the path went over a lot of places that were less populated. This is going to be the most populated eclipse in the US, with 31.5 million people able to just walk outside of their homes and experience this event. It goes through some major city centers, such as Dallas, Texas, Cleveland, Ohio, Indianapolis, as well as part of San Antonio and Austin. So there's some major cities there. So this is really different than kind of the national parks that it went through in 2017. I think the other thing about it is that folks are now excited. They've seen one in kind of recent memory. And for those of us who've seen eclipses know that you want to see your next one the second totality is over. Totality is also slightly longer in this one, and that just happens to be how the cycles happen in the eclipses. So this is also a little bit longer of observation of totality that we have.
Right.
And we're in Solar Max.
And we're also in solar max. So there's just so many things that are different about this. So what I'm hoping for is a coronal mass ejection during during that, and then aurora like 2 days later, so folks can really experience all the different things that the sun has. But even if we don't get the coronal mass ejection of my dreams, we will get have a really structured. So those wisps that you saw coming off of the eclipse pictures, there should be many of them. It should be a very complex looking sun versus the 2017. I remember 2017, there was maybe one little prominence, but we should have a much more detailed sun.
I mean, you said that lessons learned. I mean, are there big lessons learned from 17 that you think, right, we'll get this right next time?
Well, I think we got 2017 pretty right. But there's always something to learn, especially with scientists. And maybe Amir is doing an experiment for the second time, so maybe Amir would.
I mean, maybe the plane chase. I mean, did you learn something doing that? Think, right, well, approach it slightly differently this time?
Absolutely. When we ran it in 2017, it was the first time we'd ever done it with that airplane. It's not the first time an airplane's ever tried to chase the eclipse, but first time in modern history that we've done it. And I have to say it went spectacularly well, but we definitely learned things about the performance of the instruments. We learned things about how to deal with the data after the fact. And more importantly, we saw stuff that we never expected to see. We imaged the sun in high resolution in new wavelengths of infrared. And that was the genesis of the eclipse that we're now running for 2024, where we're hoping to answer some of the questions that were opened in the 2017 experiment. And undoubtedly, there will be more questions opened in 2024 that we'll have to address in 2026, 27, so on.
Yeah. Where are you basing the planes from?
The airplanes are flying out of Ellington Field near Houston,
Right.
and they will be observing the eclipse. Right now, the plan is to observe them close to the coast of Mexico near Mazatlan, but that may evolve depending on diplomatic permissions.
Can I add a little bit?
Yeah.
Many of the citizen science projects were also operating in 2017, and so are refining and their data collection and outreach methods. We also have Laura from Eclipse Mega Movie, another project with
Yes. Yeah.
cameras that operated in 2017 as well in the room. So.
Yeah.
Then we have some people in the back that may have come in after the spiel. If you're a reporter, just jump in, raise your hand, tell us who you are, and ask your question at any time. Anyone online that's waiting? All right, floor is open.
Marathon at Vox, picking up on that last point, could you elaborate on where we are in the current solar activity cycle, where we anticipate that going next year, and what effects we can anticipate from the ground, like auroras or satellite interference or what have you?
I'll take the sun, you take Aurora. That's our normal distribution. So in terms of the sunspot number is increasing. And solar max is predicted sometime late 24, early 25. Still refining models. And so for the sun, we should again see those sunspots. If you have a properly filtered telescope, we would be able to see those. And then again, when you have the eclipse, you'll see a lot of more structure from that. And then if those things do explode and have energetic particle events and flares, then CMEs, that helps you with the aurora.
I also have a citizen science project about the aurora, so that's my other hat. And we've already seen this year has been much more active with auroras and are getting a lot more reports and interest. And then the other thing about the solar cycle is that it is a broad maximum. So, you know, it's a sine wave. And so we're already in a very coming up to the max and the year after max. It's going to be a very exciting next few years for these kinds of observations and activity.
Nor, Dave, is there anything to add about how the solar max will affect observations from your missions?
For Parker Solar Probe, we will be getting out of the encounter, but we are still very, very close to the sun. And the funny thing is that Parker Solar Probe will be in the plane of the sky as seen from Earth. And Solar Orbiter will be almost on top of Solar Orbiter. They are so close to each other. And the nice thing about this eclipse is that we will get the natural eclipse from Earth, but we will get another eclipse from Solar Orbiter. Basically, we'll get two eclipses in two places at the same time. And that is probably the first ever. We never had that before.
Sorry, just explain that to, didn't quite follow that.
So, okay. The plane of the sky as seen from Earth when we are observing the eclipse, Parker Solar Probe and Solar Orbiter will be in that plane. Right. And Solar Orbiter has coronagraphs. It can image the corona, but in this plane that is perpendicular to the one seen from Earth. So basically, we are going to get two eclipses. Earth will, during the eclipse, will image the solar wind that will fly by Parker Solar Probe and Solar Orbiter. But from Solar Orbiter, will image the solar wind that is flying toward Earth. So this is an amazing time that we've never had this chance before.
I have a question, Deborah Werner from Space News. What can we learn from Parker Solar Probe's close approach? Why is this important?
Well, it's extremely important because the big phenomena that I mentioned earlier, they are there all the time and they shape the whole heliosphere around there and mainly the Earth environment as well. But the issue with them, since this plasma is propagating outward, all the processes that created them is erased by the journey. So we have to get on the spot there, make measurements there, and get the data back to understand what is going on. And again, that understanding is extremely important because it's the background solar wind that is fundamental to predict space weather. And without that understanding, our models cannot give us reliable predictions. So Parker Solar Probe, solar orbit, by getting closer to the sun, will provide us that understanding that we have been mapping forever. This is basically where Parker Solar Probe and solar orbit are getting.
What's your closest approach?
That will be on December 2024. The eve of Christmas 24, we will be at 3.8 million miles from the solar surface. Well, 3.8 million miles is a big number, but that is 4% of the Sun-Earth distance. The Sun-Earth distance is 93 million miles. We will be just at 3.8.
And your velocity at that time?
It will be 195 kilometers per second. It is 432,000 miles per hour.
The fastest human-made object, beat our own record 6 times, I might be probably.
Actually, to give you a perspective, if you pick a ride on Parker Solar Probe at that time, you can make San Francisco, DC in about 20 seconds.
And that again breaks the record, right?
Absolutely.
Yeah.
Well, I want to pull on something you said, Noor, about understanding the background solar wind to understand and predict space weather. And I think Dave can talk a little bit about the other end of that, how Oz measurements will help inform our models that predict the impacts on Earth.
Well, so the state of the sun, solar max versus solar min, inflates or deflates the thermosphere. And those have very big effects on the gravity propagation and their transport of energy and momentum from the surface to higher altitudes. So it depends on whether you're looking at the upper part of space weather or the lower part of space weather. But the lower part of space weather that's influenced by the gravity waves can move up and down very easily by quite some distance between solar max and solar min.
Does that manifest in the planet's climate in any way? Do we see a signal in weather?
I don't know that it has climate impacts, but what is interesting is that the degree to which we can predict gravity wave responses at higher altitudes may have an impact on predicting solar weather or space weather due to tropospheric influences down the road. The various weather services are getting much better at mid-scale to sort of seasonal scale forecasting. And that could play into changes in the solar weather environment as well as a consequence. If you're able to see potentially large sources that would introduce very large perturbations at small scales at high altitudes, a month or two in advance.
And again, talking about space weather, when we talk about us here on Earth, we are so lucky because we are shielded pretty well. But think when we have women and men in the moon and talking soon, they have absolutely no protection whatsoever. They are exposed. And that's why we need to understand how this stuff works. It's about.
So on that topic, presumably there'll be some consideration given to the launch of Artemis 2 and when that happens, right? Will it?
Sure.
For sure.
Yeah, absolutely.
Yeah.
Well, I'll go back to Kelly, because I like to think big too with the possibility of a coronal mass ejection during the eclipse. And you would be able to see just with the naked eye, ripples to the corona and the blast through.
You should be able to see that coming on. In 2017, I was able to see, there was like a pink filament. You see a lot of the filaments, and some of the coronal mass ejections are those filament liftoffs. So you would see that kind of pinky mass just leave the sun at that point in time. So it would be pretty spectacular.
Now, if you had one a couple days before the eclipse, is there any reason why, if you were up in Buffalo and it was a big event, that you couldn't see the northern lights during totality? Could that also be a possibility? I mean, we're talking about.
extremely
Yeah,
rare.
go buy
um,
Powerball.
Because you're, you know, it's April and you're not, well, at the time of day,
Uh.
the aurora usually maximizes on the midnight dark side of the earth. So you would kind of probably have to be further north, but it's not outside the complete, it's a very good question.
All right, thanks. This is just a basic one. When's the next, after this one, when's the next, one in the United States?
So the next one in the United States is 2045. North Dakota gets a 2044, North Dakota does get, an eclipse, but then another large eclipse, a large swath of the United States doesn't see one until 2045. So it's quite a unique event where you are. Around every 18 months, somewhere on Earth, there is an eclipse. However, it's only around 400 years in that specific location before you get another eclipse. There are some rare exceptions, Kerrville, Texas, Carbondale, Illinois. There's a few folks who had one much sooner. But that's why it's so special, is it's that experience in that place. You know, to be in Cleveland or Indianapolis, you're not gonna get another eclipse for quite a while.
There is another eclipse, it's very special. It will not be here in the US, but that one, the totality will hit the theoretical limit, which is about 7 minutes and some seconds. That will be in 2027. It will be from Western Europe to North Africa and go to the Red Sea from there. That one is 7 minutes.
Yeah, over the Luxor pyramids, yes.
Absolutely.
Right, and just so we know where to drive the Winnebago, where is the best place to go for this coming event? If you had to choose somewhere, where would you go?
So I am choosing between Cleveland, Ohio, because it has a lake effect cloud pattern that might work in our favor, and Texas, Kerrville, Texas. So those are my two choices right now.
Hey.
Does the solar max play a role in the planet's temperature at all? No, okay.
Yeah, teeny.
I'm Morgan McFall-Johnson from Business Insider. Just wondering if Parker or Solar Orbiter are gonna be looking at anything in particular during the eclipse. Is there any value in having something back during an eclipse, or is it just how it's done normally?
We have special programs. The nice thing about Parker Solar Probe that we turn our instruments and they have normal modes and they will be operating throughout rains several weeks before the very sensible days are on this. For Solar Orbiter, we have to turn the remote sensing instruments, cameras on to get us the images during the eclipse itself. And that will run maybe 2 days before, maybe 2 days after the eclipse itself. So it's continuous.
And NASA actually has our Heliophysics Systems Observatory. So we use all of our satellites together to knit the data together. So the data that Parker gets very close by can be used to validate what a mirror sees in his spectroscopy. So it's kind of ground truth, like, hey, we're actually in that. Does it agree with what we saw from the ground? And if it doesn't, that's probably actually more interesting than if it does agree. So we can be able to do that. So having multiple point measurements around the entire heliosphere really helps us during the eclipse.
Is there anything like particularly valuable about observing during an eclipse? Is it something like able to catch maybe
I was talking about photographs, but the fact that the moon is a perfect chronograph. We spend a lot of time building these instruments that try to block out the sun, because the disk is a million times brighter than the stuff that you're gonna see during the total eclipse. So we spend a lot of time doing that, and the moon is just perfect at blocking it out. So we can get down to very, very low and close to the source of those things. Whereas with some of our chronographs, we have to have a standoff distance. So we're not getting to the true source until we either are there physically or can use the chronograph openly.
Now there's, to observe the corona, you don't need a chronograph, which has instrumental limitations, or you need to be in space, which has other types of instrumental limitations. So the eclipse is sort of the best of both worlds, where you can use high-powered sensitive instruments, but you also don't have limitations of having to block the sun artificially.
There is another thing about this eclipse study. So it's this eclipse also the location of problems orbital. So we have models that try to predict the structure of the solar corona before the eclipse itself, and the validation is done by images we get during the photosphere eclipse, and these are huge because it's limited in time. But now we have these assets that Kelly talked about. We have stereo that is very close to Earth that will give us artificial eclipse for several days before. We have solar orbital on the other side, giving also artificial eclipses on the other plane. Now, instead of validating with just one view, we can validate with multiple views, and that is extremely helpful in order to validate these models that we use every day to study the corona in the perspective.
And more than that, it gives us a 3D understanding of the corona as well, because you can triangulate a lot of different structures that we see from this direction at Earth and from this direction to the solar orbiter.
So is this gonna be like the most observed, documented eclipse ever?
At least we hope so.
Yeah.
At least we hope so.
Especially if everybody gets out their phone and
Exactly.
does observations or their camera or, yeah.
And the other thing also that the occupying, we actually scientists don't advertise it that much. A lot of big science discoveries were done during the solar eclipses. If you take the coral reefing that I talked about, its origins actually dates back to solar eclipse, that is back in 1869. If you take in the first evidence that proves the relativity of Einstein, it was actually done during the total solar eclipse in 1919. So there are eclipses they provide you with opportunity to do experiments that you cannot do otherwise.
Right, but no, you'll be sampling a region that even with a coronagraph or even with the moon in the way, using instruments from Earth, you'll be sampling a region that none of those observations will be able to match because you'll be right in it on the 24th, right?
Yeah, and there is nothing that replaces going, venturing into an environment and feeling really, with every sense you have. Nothing will replace them. And that's exactly what Parker Solar Probe is doing for us now. Parker Solar Probe is rewriting the books before our eyes. There are things we learned about the solar corona that we never ever dreamed exist. If you go please to some of the slides, I'll show you some. If you flip through the slides, because there is nothing better than a visual. When you see it, you will, now, move further, more down. If you go up or down, so. Now,
Which one are you looking for?
I'm looking for the big series.
Keep going up. Oh, yeah, keep going.
Yeah, no, the one on top. The one on top. No, the one on top.
41.
Yeah, that one. So, what you are going to see there, if you play the movie, please. So what you are going to see there, this is Parker Solar Probe going around the sun and imaging the solar one that we will find you in the future. And all of a sudden, things changed completely in front of the spacecraft. This is you have it. It's one of the biggest CMEs ever recorded in history. And the funny thing that Parker Solar Probe actually flew through it. What this CME did, it cleaned everything in front of it. It left a vacuum that Parker Solar Probe traveled through. If you go to the next slide, please, you will have the audio of the CME, and I will let you just listen to it. There's an audio there.
Sorry?
Audio. There we go.
Okay, let me shut my. Is this mine?
That's yours.
This is mine.
Yeah.
It is quite, but when the shock hits the spacecraft, it's all. These are the type of things that we are getting from Parker Solar Probe that we can never ever get otherwise.
And what are we seeing? We're seeing there, what, electrons and ions flowing in a magnetic
Yes.
field lines? That's what we're
Yeah.
actually seeing.
That's a magnetic structure. It's
Yeah.
a huge bubble of ions and electrons and magnetic fields
Yeah.
all ejected out inside. And the effect of this type of structure, you can actually feel it even at the edge of the solar system. And you have the traces, they go all the way out. Pretty interesting.
About 3 minutes left. I think there's a question there. Okay.
I'm interested to know whether there are specific questions you'd like to address or, things that you would like to compare between the 2017 eclipse and the 2024.
I think the most interesting thing is structure of the corona inside. Back in 2017, the sun was in a very deep limbo. It's an unusual limbo. It was extremely bright. So the structure of the corona itself was very simple. Now, this corona is very complex. And there is data that we got just a few weeks ago from Microsoft. It's not public yet, but there is a ton of things there, and potentially it's groundbreaking, but things that we do not know it's because the corona is getting bigger.
There's also effects on the upper atmosphere, the ionosphere, that you can sense with amateur ham radio. And the ham radio folks are actually doing contests where people get out their radios and they see how many contacts they can make all over the world. And then the effect of the eclipse is like this high-speed sunset racing across the earth. And it induces some variety of waves, and some of those actually also have to do with topography of Earth. So I know that they're interested in comparing the effects there, and then there also will be some baseline differences in the ionosphere due to the fact that the sun is more active and the upper atmosphere is, changes with that as well. We have, I don't know if people want to see that backup slide with other citizen science projects, talks during AGU, but we could.
Yeah, and I also posted that list on the press room virtual bulletin board, so there's a list with all the talks.
Yeah, from various
Associated,
projects
yeah.
throughout the week. I think it's just down below here.
One more.
Yep, one more off, keep going. So I also have some organization of the different projects, but if you keep going like 2 or 3 more slides, we'll see the list of different projects and their talks, I believe.
Oh, you want the list of talks?
Yeah.
Yeah.
This one, not that you can read it, but now you can see that there are, the project itself is actually bolded there, Globe, HamSci. Yeah, actually the HamSci folks have a talk about those eclipse results like later today. So that's the 420, that's the second one there, by the PI, Nathaniel Purcell, so.
This little question for some of these citizen science projects, from just during the eclipse, when can we expect to see data? Like when's the streaming site write an article about these results?
For some of the images will be put online almost right away.
Right.
People will put them right away. But some other data, even more professional data, it takes a bit more time. Process the data, calibrate it.
For the Citizen K 2024 project, we're expecting to have a first look out basically as soon as we can. With luck, it might even be that evening or the next day. But as Noor said, the more carefully processed things will take a little bit longer, but we're putting in place data processing pipelines now to try and speed that up as soon as possible. But importantly, all of the data is going to be public, so people will be able to download that data and process it on their own or do whatever it is that they want.
And there will be some of it that's available right away. Like I know the Dynamic Eclipse Broadcast Initiative, they do have a website where people are gonna upload their effectively streams of the eclipse from different locations. And so some of that data will be available. And then to give you a sense of the, I don't know if this is the typical timeframe, but a lot of these projects that did run experiments in October, they are madly crunching and they have the talks now. So if we had AGU like 3 months after the April one, then that would be a good deadline too, but that's a good question.
When I get back to your question, what they did the difference between 2017 and 2024. So we have this model like predict the structure of the solar core. Back in 2017, the overall the growth structure of the core was reduced somewhat. But still, when you compare the images of the eclipse with the models, there are subtle differences there. But we are talking details. I think the models learned a lot from that experience, and I'm looking forward to what degree of fidelity the models can produce, even the details we see during the experiments. That would be a huge progress. I think we can prove it.
Can I follow up, what's so significant about this structure, what would you?
It's all, okay, when you look at any image of the solar eclipse, the corona is beautiful, but it's extremely complex. And that complexity is it comes basically from the complexity of the physics and the model there. And any detail you see there, that can teach you about something that is important. So getting these details is basically getting physics that is created. That's why we are getting really after the nitty-gritty things of that.
Any last questions before we thank our panelists?
Hopefully we'll be here.
Well, thank you so much, the NASA team, for this great presentation. Our next event is going to be at 3:30 here in this room. That is Disappearing Solar Wind, new results from the NASA Maven mission, aka the day the solar wind died on Mars. We hope we see you back here in an hour. And thanks again to our panelists.